Hey, we're back again. And today we are dealing with triangle similarity. Um, Before we kind of get into this, I think we need to make sure we understand what similarity means. So, if shapes are similar, it means that it's the same basic shape. It's a triangle, it's a rectangle, because rectangles can be similar. It's the same basic shape, but they're not the same size. The angles always have to be the same. So we have to have corresponding angles throughout. But the sides, they don't necessarily have to be the same. Notice that when we were doing congruent triangles, angle, angle, angle wasn't one of our options. We always had to involve a side as part of our congruence proofs. Similarity, it's not the same. Two triangles can be similar if their corresponding angles are equal. Similarly, similarly, what will happen is the side lengths that correspond to one another will in fact have the same ratio, this common ratio. So what this little diagram has shown you is we've got side A here, and side A is sandwiched. Wow, fascinating. They have actually screwed this up in this diagram. That is awesome, because side A is actually sandwiched in between numbers 1 and 2. So for this to actually work, this has to be R, and this has to be P. Wow. So we have to have common ratios. So the sides that are in between congruent angles have to have the same common ratio. And then from there, we have three, three similarity rules. And the three similarity rules are angle, angle. So if two of the angles in a triangle are the same, then the third also has to be the same because of third angle theorem. So the shapes have to be similar to one another. Next, if the corresponding sides have this relationship, we're in business. Okay? So if they have that relationship, then automatically the angles are all going to be the same because triangles are a rigid polygon. And finally, we have side angle side again. So if the two pairs of corresponding sides have the same ratio and the angle in between is the same, then we know for a fact that these shapes are in fact similar. Now, we're going to play around with it because I think that this one is one of those things where just by looking at it, it'll make more sense. So I want to know if triangle DHC is similar to triangle GHF. So the question is, are triangle DHC, I guess R is not a good phrase, I should say is similar to triangle GHF. I just introduced a new symbol to you. That tilde that floats, that's our similarity thing. If you think back to the way congruence works, similar really refers to the idea of the angles in a triangle. So we've got some things going on. Think about that tilde. Think about, so this is similar. Congruent is an equal sign with the tilde on top. Think about the connections there. Something kind of would make sense. So if these two triangles are similar, then either all three sides have to exist with the common ratio, same common ratio, or we would have to know that all the angles are the same, or we would have to have side, angle, side. Well, looking at this, we don't know anything about GF or DC. we have no clue what these two are. So we can't do the side, side, side thing. We don't know anything about these other angles. Now we could if we had some parallel lines there. So what we're gonna have to do is we're going to have to use side angle side. And that makes sense because we've got vertically opposite angles. Those angles are vertically opposite each other, therefore they're congruent. So we definitely, for using side angle side, just going to make a checklist here. We have angles that are the same. Now we have to check the ratio of those other ones. So I'm going to set this up. I'm going to see, is DH divided by GH, the corresponding sides, is that the same as CH divided by FH? This is what we're testing. If that works, we're going to have side angle side, and we'll be able to say that these two triangles are in fact similar to one another. So let's do some plug and chug here. 30 divided by 36, is that the exact same as 40 divided by 48? Okay, notice when I set this up, this is my small triangle, it's on the top, my large is on the bottom. You could set that up however you want, large on top of small, small on top of large, it doesn't matter, just so long as it's the same on both sides of that equal sign. Now, again, I'm testing this. If I divide both sides this by 6, I would end up with 5 over 6. If I divide this by 8, I would get 5 over 6. Bingo bango. So we can confidently state that yes, because of side angle side similarity. Right. So we've been able to prove it. My sides have the same common ratio, and my angle in between is in fact the same. We have that. I've got my statement, I've got my proof, and this value here is my proportionality constant. And we've done this before where we abbreviate that as K. It keeps coming up. This is why we've practiced this in the past. Now let's see if we can't look at another one before we go away here. Okay, wowza. Looking at this right here, I definitely have two triangles. There's the small itty bitty one. The small triangle is ADE. This is my small. And my large triangle is triangle ABC. So now looking at this, I guess the question I'm going to ask here is, how long is BC? So I want to know the measure of BC, or the length of BC. So first off, we got to figure out, are these two triangles similar? If they're similar, then we've got that common ratio that we can play around with. And because if they're similar, then the sides have to exist as a common ratio. There has to be that same proportionality constant. So first off, well, we know right away angle A is the same in both triangles. So actually, to help myself out, I'm going to sketch both triangles. I'm just going to put DE. I'm going to sketch both triangles out just so I make this super clear. I've got X there, I've got B, C, I've got A. So right now, I can definitively say that angle A is the same as angle A. It's the reflexive property. Angle A is congruent with itself, and that's the reflexive property. We use that whenever we have two angles that are, or two of anything that are the same. It's the reflexive property allows us to do that. Next, we're going to have a couple of interesting things. Notice that this and this are parallel with one another. Because they are parallel with one another, we've got this idea of a transversal. When that transversal cuts across parallel lines, these two angles have to be the same. And that's from our transversal rule. Similarly, it would happen the same on the other side. Now, we probably wouldn't use the transversal in this case, we'd just use third angle theorem. But we can say that we have those. So because our angles in both triangles are the exact same, we know that triangle ADE is similar to triangle ABC. That is truth. We've got that down. Now that we've proven that, we can get to work here. So, I'm just going to fill in a few more of our values. So we know that that's 5. We also know that this length from A all the way to B is 19. It's 14 plus 5, which is 19. So what that means is that in this case, well, I'm going to do this as 19 divided by 5 is the same as x divided by 10. That is because in order for them to be similar, we have to have this relationship. It has to work. If it doesn't, we're not similar, and it's just kind of sort of game over. So that has to be true. If that's true, then we can solve for x just by cross-multiplying and dividing. So 10 times 19 will give me 190 over 5 is the same as x, which is, I am way too lazy. Let's just use our calculator. 190 divided by 5. And it's right in the middle of that, and I can't see it. 38. So from this, we know that x has got to be 38 centimeters, and we were able to do all of that because we have similar triangles. So being able to show that triangles are similar, once we know they're similar, we can start doing some problem solving with that. Again, I hope this is helpful. I know it should be. And good luck.